Self-referential structures and linked list. Learning objectives. In this chapter, the user would learn the following in detail. Creation of a singly connected linked list, traversing a linked list, insertion into a linked list, deletion from a linked list. Self-referential structures. A structure can have members which point to a structure variable of the same type. These type of structures are called self-referential structures and are widely used in dynamic data structures like trees, linked lists, etc. The following is a definition of a self-referential structure. Here, next is a pointer to a struct node variable. It should be remembered that a pointer to a structure is similar to a pointer to any other variable. A self-referential data structure is essentially a structure definition which includes at least one member that is a pointer to the structure of its own kind. A chain of such structures can thus be expressed as follows. The above illustrated structure prototype describes one node that comprises of two logical segments. One of them stores data or information and the other one is a pointer indicating where the next component can be found. Several such interconnected nodes create a chain of structures. The following figure depicts the composition of such a node. The figure is a simplified illustration of nodes that collectively form a chain of structure or linked list. Such self-referential structures are very useful in applications that involve linked data structures such as lists and trees. Unlike a static data structure such as array, where the number of elements that can be inserted in the array is limited by the size of the array, a self-referential structure can dynamically be expanded or contracted. Operations like insertion or deletion of nodes in a self-referential structure involve simple and straightforward alteration of pointers. Linked lists. A linked list is a useful method of data storage that can easily be implemented in C. There are several kinds of linked lists, including single linked lists, double linked lists, and binary trees. Each type is suited for certain types of data storage. The one thing that these lists have in common is that the links between data items are defined by information that is contained in the items themselves in the form of pointers. This is distinctly different from arrays in which the links between data items result from the layout and storage of the array. Creating a singly connected linked list. Creating a new node is simple. The memory needed to store the node is allocated and the pointers are set up. Basics of linked lists. Each data items in a linked list is contained in a structure. The structure contains the data elements needed to hold the data being stored. These depend on the needs of the specific program. In addition, there is one more data element, a pointer. This pointer produces the links in a linked list. Here is a simple example. This code defines a structure named person. For the data, person contains only a 20-element array of characters. One generally wouldn't use a linked list for such simple data, but this will serve as an example. The person structure also contains a pointer to type person. In other words, a pointer to another structure of the same type. This means that each structure of the type person can not only contain a chunk of data, but also can point to another person structure. Head pointer. This is identified by a special pointer, not a structure, called the head pointer. The head pointer always points to the first element in the linked list. The first element contains a pointer to the second element. The second element contains a pointer to the third, and so on until one encounters an element whose pointer is null. If the entire list is empty, contains no links, the head pointer is set to null. Note, the head pointer is a pointer to the first element in a linked list. The head pointer is sometimes referred to as the first element pointer or top pointer. Self-referential structures and linked list. Head and tail. Traversing linked list. A linked list is a data structure that is used to model such a dynamic list of data items, so the study of the linked list as one of the data structures is important. Linked list is essentially an ordered list of some data in which one can traverse it, examine it in only one direction. Linked list is made up of nodes that consist of data section that holds the actual data and a link section which contains information about the next node in the list. Usually, that link section contains a pointer to the next node, or in array implementation of the list, an index of the next node. Usually, linked list has the following functions. Add adds an element at the end of the list. Add position adds an element at a certain position. Remove position removes a certain element. Traverse traverses the list and possibly display its content on the screen. Is empty is a function that checks if the list is empty or not, and possibly others such as get size, etc. It is important to check the position parameter when add position and remove position functions are called. Suppose the list has 5 elements in total, that is 0 to 4. It would be legal to call add or remove with position parameter in the range of 0 to 4, and also it would be legal to call add with the position parameter value of 5, which would essentially add a new node at the very end of the list after the 4th element. Thus, in the above linked list of 4 elements, node 0 has a pointer to node 1, node 1 to node 2, node 2 to node 3. Also need to keep a pointer to the first node in the list, first node, which is node 0 in the above example, to be able to access the list at all. Clearly, next is used to create a link to the next node in the list, hence the name linked list. Linked list can be represented graphically as follows. Steps for traversing the linked list. Step 1. Start at the beginning, first node. Step 2. Access node's data section. Step 3. Print out the data or does some other work per application specification. Step 4. Access the next node by using the link provided in the next section of the current node. Repeat step 2. Do steps 2 and 3 as long as the last node is not reached. Last node will point to nothing in its next section. Nothing is represented variously depending on the actual implementation. Insertion into a linked list. Adding an element to the beginning of a list. If the head pointer is null, the list is empty and the new element will be its only member. If the head pointer is not null, the list already contains one or more elements. In either case, however, the procedure for adding a new element to the start of the list is the same. Output. Create an instance of the structure, allocating memory space using malloc open close bracket. Set the next pointer of the new element to the current value of the head pointer. This will be null if the list is empty, or the address of the current first element otherwise. Make the head pointer point to the new element. Adding an element to the beginning of a list. Here is a code to perform this task. Adding an element to the beginning of a list, example. Output. Warning. It is important to switch the pointers in the correct order. If one reassigns the head pointer, first one will lose the list. The malloc function is used to allocate the memory for the new element. As each new element is added, only the memory needed for it is allocated. The calloc function could also be used. One should be aware of the differences between these two functions. The main difference is that calloc will initialize the new element, malloc will not. Adding an element to the end of the list. To add an element to the end of a linked list, one needs to start at the head pointer and go through the list until one finds the last element. Create an instance of the structure allocating memory space using malloc. Set the next pointer in the last element to point to the new element whose address is returned by malloc. Set the next pointer in the element to null to signal that it is the last item in the list. Adding an element to the end of the list. Here is the code. Adding an element to the end of the list. Example. Output. Adding an element to the middle of the list. When one is working with a linked list, most of the time one will be adding elements to somewhere in the middle of the list. Exactly where the new element is placed depends on how one keeps the list. For example, if it is sorted on one or more data elements. This process then requires that one first locates the position in the list where the new element will go and then add it. Adding an element to the middle of the list. In the list, locate the existing element that the new element will be placed after. Let's call this the marker element. Create an instance of the structure, allocating memory space using malloc. Set the next pointer of the new element to the element that the marker element used to point to. Set the next pointer of the marker element to point to the new element whose address is returned by malloc. Open close bracket, close bracket. Adding an element to the middle of the list. Here's how the code might look. Adding an element to the middle of the list. Example. Output. Deletion from a linked list. Deleting an element from a linked list is a simple matter of manipulating pointers. The exact process depends on where in the list the element is located. To delete the first element, set the head pointer to point to the second element in the list. To delete the last element, set the next pointer of the next to last elements to null. To delete any other element, set the next pointer of the element before the one being deleted to point to the element after the one being deleted. Here's the code to delete the first element in a linked list. Head is equal to head greater than next. Deletion from a linked list. The following are the codes to delete the last element and the element in the middle of the list. The following code deletes an element from within the list. After any of these procedures, the deleted element still exists in memory, but it is removed from the list because there is no pointer in the list pointing to it. This is accomplished with the free open close bracket function. Conclusion. In this chapter, we have covered the following aspects of self-referential structures and linked lists. Creation of a singly connected linked list, traversing a linked list, insertion into a linked list, deletion from a linked list.